Hello everyone, welcome to week 10. So we're now in chapter 4, which is the final chapter of our lecture notes, and the themes for the next couple of weeks are group homomorphisms and normal subgroups and quotient groups. So for this week, week 10, we're going to be talking about group homomorphisms, and the goal in this first installment of week 10's activity is just really to understand what a group homomorphism is and why we care about them. So in any area of mathematics, people tend to care about functions. And if you're studying sets of a particular type, like groups or like a set of real numbers or like vector spaces, whatever, you generally care about functions that take you from one such set to another, or indeed from one such set to itself. So far in our course, we haven't really talked about functions between groups. We've talked about various properties of groups, but we've only really mostly been dealing with one group at a time. The other comment is, when people think about functions in different branches of mathematics, usually you don't care about all possible functions, but only about those functions that have some particular properties that are of interest in the area that you're working in. So for example, in calculus, generally people are interested in functions from the real numbers to the real numbers, but not all functions from the real numbers to the real numbers, but those functions that you can do calculus with. So for example, if you're doing calculus, you probably care about continuous functions or about differentiable functions, or about functions that are continuous nearly everywhere, whatever it is, but you want your function to have some kind of continuity property in order to be able to do calculus with it. If you're studying linear algebra, you probably care about linear transformations between vector spaces rather than any old functions between vector spaces, because linear transformations are the functions that respect the linear structure that you're interested in. So similarly in group theory, we care about particular functions between groups, but not any old functions. Okay, groups are not just amorphous sets, they have algebraic structure. When we're thinking about a function from one group to another one, maybe we care about the idea that that function would somehow behave compatibly with the algebraic structures in both groups. And that's really the concept of a group homomorphism. So the concept of a homomorphism is something that applies throughout mathematics. In terms of groups, we'll say what it means, but it also applies to other types of algebraic structures. For vector spaces, a homomorphism is a linear transformation. For rings, fields, and other types of structures, homomorphisms also exist, and the precise properties they need to have depends on the axioms that hold within the type of algebraic structure that you're dealing with. So for groups, let me draw a little picture. So we're going to suppose that we have two groups, G and H, and that we have a function from G to H, which I'll call phi. So we say that phi is a group homomorphism if it has the following properties. So if we imagine our two groups as being sort of blobs, as people do when they're talking about functions, we've got the group G and the group H. We've got a function phi, which takes elements of G to elements of H. So for every element in G, so let's say we've got an element here, x of G, that phi can be applied to G, and it takes x to some image over in the group H. So if that's x in G, then somewhere over in H, we have an element which is the image of x under phi, and we would note that as usual for functions by phi of x. Also, let's say we have another element over here in G, let's say y. And then phi can be applied to y, and there'd be an element over here in H. That's the image of y under phi. So also, G and H are not just sets, they're groups. So within G, we have the potential to compose elements. And for example, we can compose x and y. And somewhere in G is the element that we get by composing x and y in G. Okay, it's another element of G. It's there somewhere. We could apply phi to that element. And if we did, we'd land over here somewhere in H at the image under phi of the composition of x with y in G. Another thing we can do is we can compose the images under phi of x and y over here in H, and that would give us some other element of H. So maybe this orange one is the composition in H of the elements phi of x and phi of y. Okay, so for any old function phi, we would not necessarily expect that if we take a pair of elements x and y in G, compose them in G, apply phi to the result of that, that we would necessarily land in the same place as if we applied phi separately, first of all, to x and y, which lands us at these two green elements over here in H, and if we then compose those using the group operation in H, which may not resemble the operation in G at all. So the requirement that a function must have in order to qualify for the title of group homomorphism is that the result of applying phi separately to a pair of elements in G, then composing their images in H, must always be the same as the result of composing them in G in the first place, and then applying phi to their composition in G. So this pink point and this orange point always represent the same element in H. Then we say the function phi is a group homomorphism. Okay, so here's the more efficient description. And a function phi is a group homomorphism if whenever we apply phi to the composition in G of two elements, we get the same outcome as if we applied phi separately to the two elements and then compose them in H in the same order. Okay, so and the key point to observe here is that the operations here, they're sort of explicitly written for a reason, that the star G operation is the group operation of G. The star H operation is the group operation of H. Typically, they won't be the same operation. So what we're saying is that the function phi not only takes elements of G to elements of H, but does so in a way that translates the group operation of G to the group operation of H. Okay, so that's a function, is a phi between groups, is a group homomorphism if it satisfies that property for all elements X and Y of the domain. So it's a special property to satisfy. Examples of group homomorphisms are kind of not as easy to write down as you might think initially, because they're such special things. But here on the next slide are a few examples that we do know about. So some examples of group homomorphisms. So first of all, the determinant function. So if we take the function abbreviated here as det, which is very standard, from the general linear group of 2 by 2 invertible real matrices to the multiplicative group of non-zero real numbers. So this R here with the multiplication symbol as a superscript, that denotes the group of all non-zero real numbers under ordinary multiplication of real numbers, which is a group. And the assertion is that the determinant function, which takes a 2 by 2 matrix to its determinant, is a group homomorphism between those groups. Okay, what does that mean? It means that if we take a pair of matrices in GL2R, so a pair of invertible 2 by 2 matrices, if we multiply them as 2 by 2 matrices, that gives us the matrix product AB, which is again a 2 by 2 matrix. And then if we apply the determinant function, that calculates the determinant of the product, that should give us the same outcome as if we separately apply the determinant function to A and B and take the product over in this group, the real numbers under multiplication of those two determinants. Okay, we know that this is true. It's not obvious. It's not obvious from the definition of the determinant why this should be true. For 2 by 2s, it's not too hard to verify it directly, but it's true for all square matrices of different sizes. It's the so-called Kushibine formula, and it is a fantastic, wonderful property of the determinant function. So yes, so what we're saying here, applying the determinant function to the product within the general linear group of a pair of matrices is the same as applying it separately to the two matrices and then doing the multiplication over in the group of non-zero real numbers under multiplication. And that's the note here. It's just kind of important to note that both the left and right-hand sides of this equation feature a product. The product of on the left-hand side is the product of AB. That's the product of two 2 by 2 matrices. The product on the right-hand side is the product of two ordinary real numbers. So the multiplication here on the left is multiplication of 2 by 2 matrices. The multiplication on the right is multiplication of real numbers, and those two obviously are not the same operation. So that's one example of a group homomorphism. So it's a homomorphism that takes 2 by 2 matrices to real numbers. It takes a non-commutative group to a commutative group, and it's a very nice and useful and important example of a group homomorphism. Okay, second example. This one comes from the study of real analysis, I suppose, and calculus, the good old logarithm function. So here, a bit of notation. We're going to let R with a subscript of greater than 0 to indicate positive real numbers and a superscript of times to indicate multiplication. This is the group of all positive real numbers under multiplication. So it doesn't include 0. It doesn't include any negative numbers. It includes all the positive real numbers. And certainly that is a group under multiplication. Okay, we can give ourselves a pair of numbers, X and Y, positive real numbers, so elements of this group. Their composition in this group is their ordinary product as real numbers. Okay, and if we define the log function, and here it doesn't even matter what the base of your log function is, you can take it to be base 10, or you can take the natural log function or whatever base you like, we can notice that the log of the product of xy is related to the log of x and the log of y, not by multiplication, but by addition. The log of the product xy is the log of x plus the log of y. So the log function, it's a function that takes all positive real numbers to all real numbers, and it has a property that the image under the log function of the product of two positive real numbers is the sum of their images under the log function. So this function is a homomorphism from the group of all positive real numbers under multiplication to the group of all real numbers under addition. Okay. The log of 1 is 0. So the log function takes the identity element of the real numbers under multiplication to the identity element under addition, and it takes the product of a pair of positive real numbers to the sum of the logs of the two numbers. So this function takes the set of positive real numbers to the set of all real numbers, and it takes products to sums. So it's a group homomorphism from the multiplicative group of all positive real numbers to the additive group of all real numbers. Okay, so it's another sort of familiar example of a group homomorphism, but where we tend to first encounter this function is not in the context of group theory. So those are two familiar and very, very useful and important examples of group homomorphisms. I want to make a few remarks, which we will develop a bit more in the second lecture for this week. First observation is that if we have a group homomorphism, so now we're back in the abstract context where we have a homomorphism from a group G to a group H, and it takes elements of G to elements of H and preserves the algebraic structure in the sense that we've seen, then the assertion is that, and this is not too surprising, I guess, that the group homomorphism must take the identity element in the domain group G to an element in the codomain H, or the target H, which has a neutral property with respect to the operation in H, and that's the identity element of H. So the assertion is that a group homomorphism will always take the identity element of the domain group to the identity element of the codomain group. So to see why that's true, if we give ourselves a group homomorphism from a group G to a group H, so think about the log function or the determinant function if you'd like to give yourself a more concrete example, and let's give ourselves an element of G. Then if we apply the homomorphism to the composition of that element X with the identity element in G, that, according to the definition of homomorphism, is the image of X under phi composed in H with the image of the identity element in G. Also, my apologies, the second factor should not be there. I'll just erase it and I'll fix it in the typed version of post the slides. So also we can observe that if we apply phi to X composed with the identity in G, that's just phi applied to X because this element is just X. Okay, so what we're saying then is that over in H, over in the codomain of the target group, phi of X is an element in there, that phi of X composed in H with the image of the identity element of G under phi is just phi of X. In other words, the image of the identity element of G under phi is an element of H which has a neutral property when composed with the element phi of X. We can compose both sides of this equation on the left with the inverse of phi of X in H. And when we do so, we cancel off the phi of X from the left-hand side. And on the right-hand side, we get the identity element in H. So our conclusion is that the image under phi of the identity element of G must be equal to the identity element in H. If you don't have the kind of patience right now to go through the steps of this proof, don't worry about it. Just remind yourself that what the lemma is saying is something that we will probably expect and certainly is plausible, that a group homomorphism must carry the identity element in the domain group to the identity element in the target group. Okay. We have a definition sort of associated with that, not entirely, but related. And that's the definition of the kernel of a group homomorphism. So if we have a homomorphism from a group G to a group H, its kernel is the subset of the domain G consisting of those elements whose image under the homomorphism is the identity element over in H. And we can observe from the lemma here that the kernel of a group homomorphism is never empty. It always at least contains the identity element of the domain. Okay, so the kernel It's a set of elements in the domain that get mapped or sent to the identity over in the target by the homomorphism. And the image of phi is what you'd expect it to be. It's a corresponding definition to the image of any function. The image of phi is a subset of the codomain or target group, consisting of all the images under the homomorphism of all the elements of G. So it could be all of H, or it could just be some subset of H. Okay, so we're going to care about the kernel and the image and the properties that they have. We will see that both of them are not only subsets, but subgroups, respectively, of G and H. And we'll see something to do with their properties, which will lead us to the topic of next week's content. Final thing here is just to I guess, interpret these definitions for the examples that we've seen. So just to go back to the definitions and recall what the kernel and image mean for these particular examples. So our first example was the determinant function from the general linear group of 2 by 2 invertible real matrices to the set of non-zero real numbers under multiplication. So here the kernel, by definition, is the set of all elements of the domain, GL2R, with the property that when we apply the determinant function to them, we get the identity element in the target group, which is 1. The number 1 is the identity for multiplication of real numbers. So the kernel here, by definition, is a set of all 2 by 2 real matrices of determinant 1. Okay, that thing has a name that I think we might have met before, but we'll meet it again here now. Anyway, it's called the special linear group SL2R. That's just the name that's given to the set of 2 by 2 real matrices whose determinant is 1. We can easily verify that it is a subgroup of the entire general linear group, which is probably a good exercise to do if you have a few minutes to do it right now. And the image then of the determinant function, well, for any non-zero real number, we can write down a 2 by 2 real matrix that has that number as its determinant. Just take a diagonal one, for instance, and we can observe that the image of the determinant function is the entire set of non-zero real numbers when determinant is applied to GL, the general linear group. Okay, so that's the first example. Second example that we had was the log function from the positive real numbers under multiplication to the set of all real numbers under addition. Okay, and so the kernel of the log function is the set of all those elements in the domain, which is the positive real numbers, with the property that their image under the log function is the identity element of the group of real numbers under addition. The identity element there is 0, the identity element for real numbers under addition. So the set of positive real numbers whose log is 0 is just 1, regardless of what the base for the logarithm function is. Okay, so the kernel there consists only of the identity element. There's an extraneous bracket there that shouldn't be there. So the kernel there is very small. It's just the identity element. The kernel in the first example was quite a large subgroup of the general linear group. And the image of the log function we can observe is the entire set of all real numbers. Every real number is the log of some positive real number. Okay, so in the next installment, which will be coming up shortly, we will see that the kernel and image of a group homomorphism of a homomorphism of groups are subgroups, not only subsets of the domain and codomain groups, respectively. And what we will look at next week, in our final week of new content, is the concept of quotient and image, quotient groups and normal subgroups. And we'll see in our next video lecture today how this relates, a little bit at least. We'll introduce it by way of looking at the kernel and image of a group homomorphism. And the basic idea is to think about how the image of a group under a group homomorphism sort of resembles somehow the group itself. So that's our kind of key conceptual idea in the next lecture. We don't have a challenge associated to this lecture. We'll have one challenge this week and it'll come along with the next video. So thank you very much, everybody, and see you later in the week. Thanks a lot.